So we have looked, this is sort of part 2 of P2 topic 6. We have looked at the hazards of working with radioactive sources. We need to maybe consider the activity and how that changes over time. If we take this source, for instance, we have in this source millions of atoms. Now, when each atom decays, it changes into another element because it's getting rid of energy and particles, and particularly when it gets rid of alpha or beta, it's losing particles from the nucleus, so it actually changes into another element that may or may not be radioactive over time. Over time, this sample will become less radioactive. Now, it's a random process. We don't know which atoms are going to decay when, but because there's so many atoms, we do see a pattern over time. And we have this thing called half-life. And half-life tells us, for instance, if we keep this simple, if there's 100 atoms in a source, I'm not going to draw 100 atoms, but let's imagine there's 100 atoms in a source, a radiation source, then the time taken for half of those atoms to decay and give out alpha, beta, or gamma is called the half-life, and we do find that that half-life is pretty consistent if we have a decent sized sample. So let's say we start at 100% of the activity, 100% of the atoms. Well, after one half-life, half of those 50% will have decayed, and after another half-life we'll have 25% which will have decayed, and then 3 half-lives would be 12.5%. So we find that the activity of radiation sources decreases over time. Now that time might be a few minutes, it might be days, years, thousands of years even. So what we get when we have a problem with nuclear power, because we have fuel rods which are radioactive, and even when they are not radioactive enough to be used in as fuel in nuclear reactors, they are still very radioactive. The half-life could be thousands of years, so we have the issue of waste and what to do with it, and we need to put that somewhere for quite some time until it stops being radioactive. So that's one of the downsides of using nuclear fission, the splitting of the atom, the breakdown of the atom for nuclear power. However, on the other hand, nuclear power does not contribute to global warming. It does not give out CO2, and we do have enough radioactive materials to power our needs for another century or two. Plenty of time, much longer than fossil fuels. So we are investing and continue to invest in nuclear power despite the risks. Quick look at background radiation. You, as a human being, are exposed to radiation all the time, some from outer space. Gamma comes from cosmic rays from exploding stars, and might come from the center of our galaxy. These come and pass through our body all the time, and we call that natural background radiation or cosmic background radiation. However, beneath our feet we also have this uranium, because we get this uranium for nuclear power from rocks, and this uranium can well, it can't move, it can't seep through the Earth's crust, but when it decays, as I mentioned, sometimes the decay products might be radioactive, and we have this gas called radon that seeps through, and it can seep through because it's a gas. It can seep through the Earth's crust, and that can cause problems because it's radioactive. The ionizing radiation can get into our bodies and cause problems. Now, certain types of rocks are worse than others. So certainly in the country, if you live somewhere, this is the worst picture of the country ever, but if you live somewhere, say in Edinburgh or Cornwall, the rocks there are allowing porous rocks, allowing radon to come through more easily than in other parts of the country. And so in places like that, in their houses, they may well vent. They will actually have an area beneath the house with a fan, and that will blow the gas up and out of the house, so the occupants inside the house aren't breathing in this radon gas. They might also have a meter in their house to measure the levels of radon gas over time. Because we're using I mean, this person here might be working in a hospital, a nuclear power station. So they might be exposed to radiation as part of their daily lives. Most of us aren't necessarily, but whenever we eat, let's say this is a wheat or whatever, this wheat or food, anything that we eat is, let's say, for instance, if we talk about some carbohydrates. Carbohydrate contains carbon, and some of this carbon will be carbon-14. What can happen is that most of our atmosphere is made of nitrogen, and when that nitrogen gets hit by a cosmic ray from outer space, it can actually turn into carbon-14, which is slightly radioactive. And so around us, that carbon-14 can then react. That carbon-14 will then join together with oxygen and make carbon dioxide. But it's carbon-14 carbon dioxide. Plants will absorb it during photosynthesis, and we will then eat the plant's carbon-14. Might form part of that carbohydrate. So we are taking in some radioactivity in our food all the time, and the levels of carbon-14 as we breathe out the CO2 would have some carbon-14 in it, stay constant in our body all our lives until we die, the half-life being about 6,000 years. So if we find a bone which has got a 50% amount of carbon-14, the half-life, we know that bone is about 6,000 years old, or 25% of carbon-14. That bone is about 12,000 years old. So we can use carbon-14 to date things. I'll leave it there for now. Thank you for listening.